Welcome to the course on computational fluid dynamics. Many of you in your undergraduate and postgraduate days would have taken a course on fluid mechanics or momentum transfer. You would also have taken a course on computational techniques, where you would have learned how to solve equations, for example a set of algebraic equations or a matrix equation type of problems, and root finding of nonlinear equations, partial differential equations, ordinary differential equations, and so on. This course, computational fluid dynamics, it derives both from fluid mechanics and also from computational techniques, and comes up with a set of numerical methods which will enable us to solve the equations which govern the flow of a fluid in any domain. And this enables us to go much beyond what we can do in analytical part of a fluid mechanics course. In fluid mechanics we have studied how flow goes through a straight pipe and how flow goes over for example a sphere under creeping flow conditions, and what type of velocity profile we have for flow over a flat plate. In such simple geometries we know how the flow takes place, and we can characterize the pressure drop or the drag coefficient or the friction factor in such simple cases. But we know that when we want to deal with practical problems, we have a difficulty in extending what we have learnt in a basic fluid mechanics course to complicated geometries. And the complicated geometry need not be very complicated. For example, if you have a room like this, and as an engineer you want to put an air conditioner. So the question would be that you would pose yourself is that where would I put the air conditioner in order to have maximum effectiveness? And so if you want to answer this type of question, you would have to know how the cold air from the air conditioner would flow in this room, and what sort of coldness it would give to people occupying people in different places. So you would have to understand in such a case the buoyancy related flow which is induced by cold air flowing from the air conditioner, and that is a complicated problem that you cannot deal with from what you would have known and learnt in a basic course in fluid mechanics. If you take another example, like you have a chemical reactor, we take the simplest case of a cylindrical vessel which is half filled with one reactant, liquid reactant, and another liquid reactant is being poured into it, and the two have to, let us say that there is a density difference between the two. So if you were to leave the two reactants like that, the lighter fluid would go to the top and the heavier fluid will go to the bottom. You want to have these two mixed together in order to have a reaction which we want to take place in this reactor. So what could we do? We could put an impeller to an agitator to mix the two fluids. The question would be, what should be the type of the mixer, what should be the type of the agitator, where should we place it? And you also may want to put a catalyst for this reaction to be catalyzed, okay, to be enhanced, and in such a case you would like to have the catalyst thoroughly mixed. So you may want to, you are not only interested in how the two immiscible liquids come together, but you would also like to know how the catalyst, which may be in a solid form, would be dispersed within the liquid media. So again the question would be, what kind of impeller you would like to put, and where would you like to put, at what velocity you would like it to rotate, so as to achieve the task of good mixing, ensuring good contact between the various phases, but without spending too much in terms of the cost of the impeller, which is an initial investment, and also the cost of maintenance in the sense of what is the power which is required to keep this impellers rotating at the given speed. So if you want to look at the overall cost from a designer's point of view, you would have to know how the fluid is taking place within this, and how the solid particles are moving along, and what is the distribution that is achieved, and under what ideal conditions, optimal conditions can we get the best mixing with as little power consumption as possible. So you may, in such a case, again your basic knowledge of fluid mechanics will not be able to give us much information on this. One may do experiments, but experiments will be very costly. So again there is a requirement for us to know how fluid flows in situations which do not fall into one of the ideal categories, like fully developed flow in a pipe, or flow over a infinitely long flat plate, or flow over a sphere or a cylinder which is submerged in an infinite expanse of the fluid. So these are all cases which are very simple, but when we look at the practical situation, we may have much more complexity. We can take another example, common example. Let's say that you have a internal combustion engine, and inside that you know that you are sending fuel, and the fuel typically liquid fuel, which is sent in the form of fine droplets. These droplets would evaporate, and then there would be a combustion, and the combustion would release energy, which is then used to drive this internal combustion engine. As an engineer, you would like to know what is happening inside the engine, so that you can control not only the delivery of the power, not only the amount of power that you are able to extract from this, but also you would like to control and minimize the formation of undesirable products like pollutants, for example the nitrous oxides, and if you have some sulfur dioxide and those kind of pollutants. And in order to do that, you would have to look at how the fluid is being injected into this, and how it is vaporizing, and what kind of disturbance to the flow field that is obtained from this vaporization, and how the vaporized fuel and the oxidant, that is rest of the air, are mixing together, and how they are combusting, what kind of heat is being released, and how the heat is being diffused into the rest of the domain, and what are the conditions in which chemical reactions are taking place for this combustion to take place, and what are the conditions that are prevalent in which these trace species like nitrogen oxides are formed. So there you are looking at a combination of fluid flow together with heat transfer, together with chemical reaction, and lots of time scales and length scales are involved, and all this is happening while the piston is moving up and down. So that's a very complicated situation, and one can never hope to get any kind of simplistic solution that for this kind of complexity. But if we have generic specialized tools which constitute the body of computational fluid dynamics at our disposal, then it is possible to represent this transient turbulent chemical reacting flow simulation to be done in a computer, and from this we can derive some information which will be useful for us as engineers. We can control the rate of fuel injection, at which point we inject the fuel, at which point of time we inject the fuel, and in what form we inject the fuel, and how the rest of the power transmission and heat transmission is taking place. It is possible to simulate all these things in the computer, so that we can therefore make modifications to the processes, to the process that are in our control, to derive the best performance from the engine, whether it is in terms of fuel economy, or whether it is in terms of the delivery of the power, the smoothness of delivery of power, or in terms of pollutant formation, and so on. And there is also the other more chemical engineering aspect of this internal combustion engine, that if you want to put a catalytic converter so as to absorb the pollutants that are produced in that, then again you are looking at some further chemical reaction that is taking place inside a reactor, through which the gases, the exhaust gases flow. So you have to make sure that there is good contact between the exhaust gases and the surfaces at which the chemical reaction would take place, and you would also need to make sure that there is enough provision is there for this to happen optimally without too much of pressure drop, so that the back pressure would not be built up to so much, and without any bypassing of the gas. If there is some part of the exhaust gas which is not able to get into contact with the solid surface, and if it is not able to participate in the chemical reaction, then that part of the pollutant which is there in this bypassing gas will not be converted, so that will come out in the eventual exhaust. So again there is a need for us for an engineer to know how fluid is flowing through this catalytic converter. So these are typical type of fluid flow situations that are encountered by an engineer in the daily profession, for which one would like to know answers to the flow of the fluid along with flow of the heat and chemical reactions that may be taking place. And if we need to answer these questions, we cannot rely on what we have learnt in our basic courses or advanced courses in heat transfer and transport phenomena. We have to be able to go beyond what we can do with analytical techniques. So this is where computational fluid dynamics steps in. So computational fluid dynamics, as the name implies, is a subject that deals with computational approach to fluid dynamics, and it deals with the numerical solution of the equations which govern fluid flow. And although it is called computational fluid dynamics, it does not deal just with the equations of fluid flow. It is also generic enough to be able to solve simultaneously together the equations that govern the energy transfer, and also the equations that determine the chemical reaction rates and how the chemical reaction takes place and how mass transfer takes place. All these things can be tackled together in the same overall format. So this framework enables us to deal with very complicated flow situations in a reasonably fast time, such that we can get a simulation, for example in a few hours time, or in an overnight computation, and for a given set of conditions an engineer would be able to simulate and see how the flow is taking place and what kind of temperature distribution there is and what kind of products are formed and where they are formed, so that he or she can then make changes to the parameters that are under his control to modify the way that these things are happening. So in that sense, computational fluid dynamics, or CFD, becomes a great tool for a designer, for an engineer. It is also a great tool for an analysis, for a post-mortem of a reactor or an equipment which is not functioning well, because in typical industrial applications many things may be happening, and what a designer has had in mind at the time of fabricating or designing the equipment may not be actually what an operator of the equipment introduces into the equipment at the time of operation, maybe after 5 years or 10 years. Changes might have taken place in between, and in such a case the performance of the equipment may not be up to the standard, and you would like to modify it in such a way that you can get better performance. So the question is then, what has led to the fall in the performance, and what kind of measures we can make without making an overall change in the design and equipment, within what is within the means of the operator to control. Is it possible to get better performance from the equipment? Is it possible to increase the productivity? If you want to look at these kind of what if kind of analysis, then again computational fluid dynamics, a well built computational fluid dynamics model will be able to answer these kind of questions. So we can see a role for CFD both in the initial design of industrial equipment and also in the day-to-day operation, and also in the case of what if kind of scenario investigations. So this makes CFD a very versatile tool in the hands of engineers and also scientists. One would say that scientists would be interested in knowing, for example, what may be happening in a very small micro scale reactor. If you take a micro reactor, one would like to know what may be happening in that, and it may be very difficult to do experiments in those conditions, and a scientist may be interested in the very fine transient of a particular phenomenon for a particular situation, and it may be very difficult to get an experimental non-intrusive measurement of the same. So even for a scientist, CFD would make a very good sense as a tool for analysis. So in that sense, one would say that CFD is a very useful tool, and over the past 2 to 3 decades, CFD tools have become so specialized and finely tuned, finely honed, that they now have become an indispensable tool in the hands of engineers for a range of industry applications, all the way from aerospace to metallurgy, including chemical and mechanical engineering, civil engineering, environmental, biological process, and so on. So in this course, we are not going to look more on the applications on how we can make use of the CFD codes, but we are going to look primarily at how we can get a solution to a set of equations. We are going to look at what kind of equations we need to solve in order to answer these kind of problems, and how we can solve these equations using CFD. We will also look at obviously why we cannot solve them using analytical methods. Then we will see how we can solve this using CFD techniques. What we should keep in mind is that CFD is not mathematics. It is a special set of techniques which are ideally tuned for the solution of a specific type of equations that occur in fluid flow is a subject of interest. So it is not general mathematics that we are interested in. We are interested in looking at special techniques which have been developed to solve these equations in a very efficient manner. It is those techniques that we want to do. So we will see that it is not a simple solution like that. We look at what constitutes a CFD solution. We have a wholly different philosophy of answering a question that you have as a particular flow domain. What is a flow field? So let us start with a simple example, so that we can try to differentiate between an analytical solution and a CFD approach. So in this introductory lecture, we look at a problem which is solved in the CFD way for a very simple problem. Okay, for this simple problem we probably do not need to use CFD, but we will show how we solve it using CFD so as to bring out the difference between an analytical solution and the CFD solution, and then we will elaborate what more we have to do in order to solve the general problem. So at the end of that we will have a good idea of what CFD is about, and we will be able to give an outline of what we are going to do in the rest of the 40 to 45 lectures. So let us start with an application of the CFD for a simple problem. The problem that we are looking at is a fully developed steady flow through a duct which is rectangular in cross section. This is a case for which analytical solutions do exist, but these analytical solutions are obtained in a difficult way. We may have to do conformal mapping of the geometry from a rectangular domain into a circular domain, and then we can get a solution to that. So it is beyond the scope of an ordinary the general syllabus that is taught in undergraduate chemical engineering. So we will see when we try to use CFD techniques for this, we do not have to go into sophisticated mathematics. With the simple mathematics that we already know, we can generate a solution, but the method of generating the solution is not something that is amenable to handheld calculation. It is amenable only to a computer based calculation. So this is where computational approach comes into picture, and it is only with the advent of fast computers with cheap memory that we are able to solve a large number of industrial problems using CFD techniques. If computers had not been there, or if computers had been there but they were very expensive, then CFD could not have spread to lots of industries. It would have still remained in sophisticated labs in elite institutions. So it is the bringing together of a robust set of numerical methods for the efficient solution of equations, the easy availability and of fast computers with loads of memory storage capability, that has really given rise to the development of CFD as an engineering tool. So we will just look at, we will start with looking at the simple case of flow through a rectangular pipe. So what we are looking at is a pipe of rectangular cross section. So this is an infinitely long pipe and we have taken a section here. The flow is fully developed. Let us fix some coordinates. We can put x here, y in this direction and z in this direction. So this is y and this is z. We have chosen here a right handed coordinate system such that if you rotate the x axis about the y, the z is in the direction of a right hand threaded screw like this. So this is the notation that we have, and along with this xyz notation we denote the respective velocity components as u, v and w. So the u velocity component is the velocity component in the x direction, v is the velocity component in the y direction, and w is the velocity component in the z direction. And the problem that we have is the flow is steady laminar and fully developed. And under these conditions we know that u is equal to 0 and v is equal to 0 throughout, and we are interested in the flow is essentially two-dimensional in the sense that only w is the non-zero component, and the w is a function of both x and y, and it is not a function of z, and it is not a function of time. So the flow is steady. So w is the only non-zero component of the velocity, three velocity components, because its flow is steady and fully developed and laminar, and it is not a function of z. So at any cross section the flow field, that is the variation of w with x and y, will be the same, and it is steady and it is two-dimensional in the sense w is a function of x and y. So the problem that we want to know is how does w vary with x and y. So this is the flow field that we are interested in. As I mentioned, there are analytical solutions to this, but we are not interested in the analytical solutions. We would like to do this using computational fluid dynamics approach, and this is a simple case because there is no time dependence and there is only one velocity component and it is a function of both only x and y, and the domain is such that the flow domain is such that it fits into a Cartesian coordinate system x, y, z. So in that sense it is a simple problem, and we would like to solve the simple problem for the sake of illustration as to how CFD works. Now what do we mean by how CFD works? So in CFD we solve the governing equations using numerical methods. So first of all we need to find out what is the governing equations, or what are the governing equations. So in this particular case we will show later on that the governing equation is given by, we are putting it as G if a governing equation as dou square W by dou x square plus dou square W by dou y square times mu, where mu is the dynamic viscosity, is equal to dP by dz, where dP by dz is a constant it is negative in the sense that as z increases pressure decreases, so it is a negative constant. So we can put this as some minus c, for example, where c is a positive quantity. So c is a constant and pressure gradient is constant because it is a fully developed steady flow in the rectangular duct. So right now we do not have to worry about where this equation has come from, okay. We only say that this is a governing equation, and the governing equation is, we can see, is a partial differential equation. So this requires boundary conditions. Since the flow is steady, there is no time derivative, so it does not require initial conditions. So what will be the boundary conditions for this? We need to look at the variable that we are solving for. The variable that we are looking at is the W component. So we need to know what is the W. When we talk about boundary conditions, what is the value of W on the boundaries? So the flow domain of interest is this domain, and we know that for fluid flow which is bounded by these walls, we know that the most obvious, most applicable boundary condition is the no slip condition. So we can say that W is equal to 0 on all walls. So this is the second part of the specification of the problem. So we now have a mathematical problem which is specified, that is this equation with a given value of constant. So this is given here, and with the boundary condition that W is equal to 0 on all the walls of this specifies the mathematical problem. Given this problem, we want to know if this is the case for a given dynamic viscosity, for a given pressure gradient, and for a given domain, for example of length, for example capital X, and for height capital Y like this, what is then the variation of W at any x and y. So this is the mathematical problem that we want to solve. So this mathematical problem is solved in CFD not like this, okay. It is not solved exactly like this. So at the end of the CFD solution we won't be getting W as a function of x and y. So in the CFD approach, okay, we don't get W at xy. Instead of that, we give the value of w at, loosely speaking, xi yj, that is where xi and yj are the coordinates of points which are spread within the computational domain. So instead of saying that, instead of seeking a solution of w as a function of x and y, which is a continuously variable, we are giving a solution of w at discrete points which are spread throughout the domain. Okay, so we give w at discrete points spread throughout the domain. And if you want to have a solution at a point which does not coincide with any of these points, for example, we have these things. Typically we give at several points which are in a fairly ordered logical sequence like this. So at these points marked by the crosses, we give the solution. And if you are looking for a solution at this point, we don't get it from CFD directly, but given that the solution is known at these neighboring points, we can get it by interpolation. So we do not derive the value of a solution at any x and y, we evaluate the value only at specified points which are known as the grid points. And so we are not getting a continuous solution, we are getting a discrete solution, but the points at which we are evaluating are in our control in a way. Okay, we decide where to put where to evaluate the points, but at the same time we don't have total control. We, for example, we cannot say that in this overall domain I want at this point and this point, this point. We are forced to have the solution at several points, at many points within the overall domain. Typically it may be 1,000,000 points within the domain. Only by evaluating the solution at 1,000,000 points may we have to get can we get an accurate solution. So the first point that we would like to know about a CFD solution is that the solution is obtained at discrete points, discrete pre-identified points which are spread throughout the domain. And if we want to get a solution at any point in between, we have to do it by interpolation or extrapolation as necessary, typically interpolation. And if there are other points of interest, for example, if we want to get the shear stress or the heat transfer coefficient, so that information can be derived from these values which are obtained as part of the solution. For example, the shear stress is given by the gradient of velocity. So since we know the W at several points, we can evaluate the gradient and we can multiply with the viscosity and then we can get the shear stress. So in that sense we are going from a continuous solution to a discrete solution. The second point that we want to emphasize about CFD is that we are not giving a solution which satisfies the governing equation exactly. So we are giving a solution which satisfies the governing equation and the boundary conditions approximately. Okay, so we are not getting an exact solution of the governing equation, we are getting only an approximate solution of the governing equation. Again here, as the solution seekers, we have some control over what will be the approximation. We can reduce, for example, the error in the solution that may be expected. We do not know the exact error because we do not know the exact solution. So we can reduce the error, possible error between the CFD solution and the exact solution of the governing equation by choosing large number of points or by changing the way that we approximate the equations. Okay, so we do have some control over what will be the how to reduce the error, and that gives us some satisfaction that of getting a solution. But we should keep in mind that the solution that we are getting from CFD is an approximate solution of the governing equation, and it is not guaranteed to be an exact solution. It may be an exact solution under special cases, but in general it is an approximate solution. So how do we generate this approximate solution like this? So there are several ways of doing it, but for the sake of illustration, the way that we try to do is that we take the partial derivative here, and for each derivative we substitute an equivalent approximate finite difference approximation, finite difference formula for it. For example, if you have dou square w by dou x square, then at a particular point I comma j, if this is the point that has to be evaluated, then we can write this roughly as w at I plus 1 comma j minus 2w I comma j plus w I minus 1 comma j divided by delta x square. Now this requires us to what we mean by this I comma j and all this. So we will go back to this domain here. We choose the points that we want to evaluate in this finite difference approach, in this approach, at points which are, for example, which are uniformly spread here, and which are also intersections of lines of constant x and constant y. For example, this is line of constant y equal to 0, this is y equal to 0, y equal to capital Y, like that, and this is a line of constant x. So this point here is an intersection of constant x line and constant y line. So we can, the I and j here denote the ith constant line in the x direction and the jth constant line in the y direction. So for example, we can put this to be I equal to 0, this is 1, 2, 3, 4, 5, 6. So we have these lines, out of which the 0th line and the 6th line constitute the left boundary and the right boundary of this. And similarly we can put j equal to 0 as the line corresponding to the bottom boundary, and this is j equal to 1, 2, 3, 4. So we have divided the domain into 1, 2, 3, 4, 5, 6 divisions in the x direction and 4 divisions in the y direction, and so therefore there are, at intersection of each of these lines there are points, and at these points we want to evaluate the w. Okay, and we see that some of these points lie on the boundary, and at that point we already know that w is equal to 0. So this is known as a Dirichlet problem, where the value of the variable that we are evaluating is specified on the boundaries. So in that sense, these are the values, these are the locations at which we do not need to evaluate w because it is already known. At all these points we do not need to evaluate, we only need to evaluate the values in the interior. So when we say, we can now take an ith x equal to constant line and a jth y equal to constant line. So this is y equal to constant line, and this is ith x equal to constant line. The intersection of this here, this point is the I comma j point. So the point is denoted by the index I denoting the ith coordinate constant coordinate line in the x direction, and j indicating the constant coordinate line in the jth direction. So under these conditions, assuming uniform spacing in the x direction and uniform spacing in the y direction, we can write an approximate formula for the second derivative in the x direction like this, where this value is being evaluated at ij, and this is I plus 1j. So that is, now we are looking at this particular point. So this is w I plus 1j means this point here, w I minus 1j is this, and w I j is this. So we are approximately writing, we have a formula for writing this, and this is a formula which is one of the many formulas, and we will be deriving how to do this approximation later on. We will be deriving this in later parts of the course. Similarly, we can write another approximation for this, dou square w by dou y square at the same point I comma j can be written as w I j plus 1 minus 2w I comma j plus w I j minus 1 divided by delta y square. Okay, so this again is an approximate formula for the dou square w by dou y square at I comma j. So now we can take this equation here, replace this derivative by this formula, and replace this derivative by this formula. If we do that, what we get is an algebraic equation. The resulting equation will not have any partial derivatives, it will only have these variables w at several points within the domain of interest. So let us do that. We will take, for the sake of simplicity, mu here, and put this as c by mu as some constant k, c1. So we can say that dou square w by dou x square plus dou square w by dou y square equal to c1, where c1 is 1 by mu dp by dz, can now be written as w I plus 1 comma j minus 2w I comma j plus w I minus 1 comma j by delta x square plus w I j plus 1 minus 2w I j plus w I j minus 1 by delta y square equal to c1. Here delta x is the spacing in the x direction and delta y is the spacing in the y direction, which is known. c1 is a constant again which is known, and so we can rearrange this and write it as 1 by delta x square w I plus 1 comma j plus 1 by delta x square w I minus 1 comma j minus 2 by 2w I comma j 1 by delta x square plus 1 by delta y square plus w I j plus 1 1 by delta y square plus w I j minus 1 1 by delta y square equal to C1. And what we see here is that these are the variables and each of them has a coefficient 1 by delta x square like this. These things, the coefficients are some things that we can do. So we can rewrite this expression as Aij okay, is equal to 0, okay, where this is an algebraic equation, and this algebraic equation here is an equation for point ij. So in this equation there are the coefficients here 1 by delta x square, delta y square and all those things, they depend on the particular values of the variables that come in this particular approximation. So if you were to look at this case, we will just take a generic point like this. These are lines of constant x, these are lines of constant y here. If you are looking at I here and j here, so this is the point that we are looking at. So we can see that this has this value is appearing in this equation, and the neighboring value to the right and the neighboring value to the left and the neighboring value to the top and the bottom. So these 5 are the variables unknowns which are appearing in the equation for the point I comma j, and similarly we can derive a similar equation for all the points at which we want to know, we want to find the value of variables. So that is for all these points, at each of these points we write the same finite difference approximation for the derivative, and each of those approximations will give us an algebraic equation like this. So if we have here we have 15 points, okay, so we will have 15 algebraic equations for the 15 variables w1 this point, this point, this point like this. So at the end of that, this partial differential equation is converted into an equation like AW equal to B, where A is the coefficient matrix and W is the set of unknowns, that is W11, 21, 31, 41, 51, and then 12, 22, 32, 42, 52 like this. So we will have a set of 15 equations, 15 algebraic equations for the 15 unknowns, and the unknowns are the value of W at the 15 grid points. In this simple case, the 15 equations that we are getting are linear equations in the sense equations in which these are the variables which have the coefficients of which are constants. Delta x is a constant, delta y is a constant, so all these things are constant. So what we have ended up for this particular problem, this partial differential equation is converted into a matrix with matrix of 15 variables with constant coefficients, and as part of this substitution, which is known as a discretization step, we not only have the value of the coefficients Aij, but we also have, this is not 0 here, this is, let us say Bij, okay. So we also have the value of the B for each equation, And there are several methods for the solution of these matrix equations, and there are for example direct Gaussian elimination is one direct method which is fairly widely practiced, and then we also have iterative methods like Jacobi method or Gauss-Seidel method and so on. So there are several techniques for the solution of AW equal to B. When we do this inversion, so from this we can get W, that is we can get W at xi by j. So this is how we are getting a solution in the CFD approach. We are not solving the equations directly, in the sense that we are not, for this governing equation and for this boundary condition, we are not getting W at any xy, we are getting only at the selected grid points. And not only that, we are not getting the value of this W at xi by j by solving the exact equation. We are solving only an equation which is an approximation of this governing equation, because we have made an approximate formula for the for the two derivatives. So in that sense, in the CFD approach, we convert the governing equation into an approximate set of algebraic equation, and then we solve it to machine accuracy or to some degree of accuracy using numerical methods, and that will finally give us the solution at the pre-selected grid points which are spread throughout the domain. So this is how the CFD approach works, and we can see that in the process of generating the solution we have not really used a lot of mathematics that we are not unaware of. Okay. So these approximations, finite difference approximations, are fairly well known, and the conversion of substitution of this and conversion of this into the matrix equation is just a question of good bookkeeping. It is not very difficult once we evaluate these formulas, and the solution of the matrix equation is also not very difficult. So in that sense we are not on unfamiliar territory for this simple case. Okay. But when we look at the general case, when we look at the real three-dimensional turbulent reacting flow case, then many aspects of this solution become much more complicated, and that is where CFD comes into picture, because for a simple problem we are looking at 15 equations, but if you want to get good accuracy, then we need to put lots of points. We would ultimately like to get a solution of W x and y which is very accurate. So that means that the approximation of this PD into the corresponding difference approximations, this has to be very accurate, and that is possible if we have large number of points. The more the number of points that we have, the better will be the accuracy. So we should have large number of points, and what that means is that the size of this matrix equation, the size of this coefficient matrix A becomes very large, and instead of 15 equations we may have 1500 equations or 15,000 equations. So as the matrix size increases, the solution of this here becomes very problematic, it becomes very time consuming. So we need to have very efficient solution methods for the solution of these equations. So that is one difficulty. When we have a more general problem, we normally do not have a single equation, we have 3 equations, for example for a general 2-dimensional flow, or 4 equations for an isothermal non-reacting flow, a laminar flow. Okay. So that means that you do not have a single variable, but you have 4 variables, and we have to solve that thing 4 times. And not only that, we will see that the equations are not in such a way that you can solve them separately. If you want to solve the 4 equations which govern, which are called the Navier-Stokes equations, you cannot solve them individually, you have to solve them together, and that makes it a problem for the solution. So, and not only that, in the general case this sort of approximation does not give us linear equations. For the simple case of this type of Poisson equation, we got a linear algebraic equation. In the general case, we have nonlinear algebraic equations, so the solution of which is even more difficult. And so there are, and when you look at a general domain, not something that fits into this xyz coordinates like this, then identifying the points at which we want to get the solution and spreading them throughout the domain, that itself becomes a problem. So every aspect of the solution, that is from the equations and finding the corresponding approximations and spreading the points throughout the domain, converting this equation into an algebraic equation, and then the solution, every part of this becomes much more difficult as we go to the general case. And this difficulty is what has driven lot of developmental activity towards finding specialized algorithms which are needed for each of these steps, and that is what constitutes the body of CFD, and that is what we should be aware of in order to get a CFD solution for the general case. When we do that, then essentially the world is at our feet, and we can use these techniques for the general case of fluid flow in any type of situation. So in the next class we will illustrate one method which can be used for the solution of these equations. We will work out an actual problem so that we can get a real feel for this, and then we will take it further to discuss the case of generic fluid flow solution. Thank you.